The next common type of sequence is called the geometric sequence. Now you can think of geometric as having the same tendencies as an exponential function. So if you remember in the table form, an exponential function will be multiplying by the same number over and over again. So here we've got it multiplying by 3 over and over and over again. And remember, then we start with 0, 1, and 2. However, in a geometric, it's going to be just a list. And you'll notice that your loop-de is still going to be that you're multiplying by 3 over and over and over again. This thing that you're multiplying by every time, we call this the common ratio. Now this is going to be, the equation is going to be a little bit different. We're used to seeing y equals a times b to the x. Remember, a is that y-intercept, so a would be right there, and then b is your loop-de number. But what happens is, if you remember, instead of y we use a sub n, and then we're not going to have a 0. Remember, we always have that where it starts at 1, a sub 1. This is a sub 1. So instead of a y-intercept, we're going to have a sub 1. And then we're still going to have that loop-de number. This time it's an r. We call it the common ratio. But instead of having just an n up here, because we're starting with our first term and not our 0th term, our loop, or in our exponent, we're going to have n minus 1 to take care of that. So let's look at an example. Write a rule for the nth term if you have the sequence 8, 4, 2, 1. So it's actually not all that difficult. If we first figure out what is r. Now if you can't figure out r just by looking at it, we can tell that we're multiplying by 1/2, and it's always multiplying. Okay, but if you can't figure that out, what you can always do is take the second one divided by the first one. So 4 divided by 8 gives us 1/2. Okay, so you can always just take a second one in the line divided by the first one before it in the line, and that'll tell you your loop-de number. And so my equation is a sub n equals, remember now we start with our first term 8, times the loop-de 1/2, and then instead of just to the n, we're going to go n minus 1. That way we can have a sub 1 there instead of having to go back in the line. And so this would be my equation. We don't have to worry about simplifying at all. This is the rule. Now we can have one that's a little bit more difficult. So let's say we have that r equals 6, and we're told that a sub 3 equals 72. And now we need to figure out the general rule. Well, we have to figure out a sub 1. We don't have that. So to do that, we're going to start plugging into our equation and plug in what we know. So we're going to use this as our temporary stuff. So a sub 3 is going to go right there, but instead of putting a sub 3, I'm going to put what its value is 72 equals. I don't know a sub 1. R is 6. To the n minus 1, n here is 3 in this example. So we have 72 equals a sub 1 times 6 to the second power. So 72 equals a sub 1 times 36. Divide both sides by 36. And we've got 2 equals a sub 1. So now I can write my equation, a sub n, or my rule, equals the first term, which is 2 we found, times my common ratio of 6 to the n minus 1, and that's our answer. Now I just want to point out, because I know this is a common mistake, a lot of times people want to multiply these numbers, but remember we have to do exponents first, so until I figure out what this is, I can't get rid of the 6 and take it times anything. So this is exactly what you should be leaving. So now we want to work on our series. Now a series is when you take that sequence and you start adding it together. You have two different kinds of series. You have the finite one where it ends somewhere. So that one is going to be s sub n, because n is where how many terms you're going to add up, equals a sub 1 times 1 minus r to the n over 1 minus r. And so, and that's it. But if we look at an example, I have 3, 6, 12, 24, and so on. Now, if I was to add up, let's say, the first 5 terms, and that's just so that we have something simpler to work with here. We have s base 5 equals a sub 1 is 3 times 1 minus, if I look at my r, if I look at multiplying here, I'm multiplying by 2 every time, so 1 minus 2 to the 5th, because it's 5 terms, over 1 minus 2. And then as we go and do the math here, this would be 3 times 1 minus 32 over 1 minus 2 is negative 1, equals 3 times negative 31 over negative 1, which is 3 times 31, and that gives you 93. And we could easily check that by figuring out the next term and then actually adding them together. The other type of series is an infinite series. And this gets a little bit tricky because it doesn't work for everything. So here's how it goes. The sum without the n, because we're not ending, it keeps on going forever and ever, equals the first term over 1 minus r. Now, if I was to go back to this one and use that for my infinite series, you would find that it would give you a strange answer. I think it even gives you a negative answer. And that's because, think about it, if I was to take this and add it up forever and ever and ever, I would never get a sum because it keeps getting bigger and bigger and bigger. The only time this works is if it's a decay. Remember a decay in the exponential functions. R has to be less than 1 for this to work. So the only time you're going to use this then is if r is less than 1, and then it'll actually converge into a sum if you go on for infinity. Okay, we have one more thing to look at. Have you ever wondered how you can take a repeating decimal, so let's just say we have 0.6 repeating, and turn that into a fraction? It's pretty easy to take a fraction and turn it into a decimal and see that it's repeating if you take a calculator. But what about the other way around when you have a repeating decimal? What we can do is we can turn this into a series. So this would be 0.6 plus, remember this just has 6's going on and forever and ever, so 0.6 is taken care of right there. This one is 0.06 plus, this one is 0.006, this one is plus 0.0006, and so on. And so if we use our infinite series, sum of the series, here, if we use that, we can actually figure out what this is a fraction. If we look at our loopties here, we're multiplying by 0.1 every time. So we can do S equals, a sub 1 is 0.6 over 1 minus r is 0.1. So this is 0.6 over 0.9. Move the decimals over, I have 6 over 9, which reduces to 2 over 3. So 0.6 repeating is really 2/3, which hopefully you knew ahead of time. But you can do that with any repeating decimal, is you can set it up as a series first, that has that pattern, figure out your loopty, and then just plug it into that infinite series.